Welcome to the Deep Dive. Today we're looking at physics, and our sources show this really stark contrast. On one side, there's this deep theoretical crisis brewing, but on the other, an incredible engineering sprint.
It really is a fascinating tension. Kind of the core question we want to unpack is how both these things can be true at the same time.
Right. How can our fundamental ideas about the universe be, well, wobbling, while we're building fusion reactors faster than ever?
Exactly. Because the foundations, the standard model for particles and Lambda CDM for cosmology, they're both facing serious challenges. And the biggest hook, maybe, is that we seem to be fundamentally misunderstanding the universe itself.
Okay, let's start with the universe then. The big one is the Hubble tension. That's the mismatch in how fast the universe expands now versus how fast we thought it expanded way back when.
And for a long time, the hope was maybe it's just measurement error. Tricky calibrations.
But the latest data from Webb and Hubble seems to have shut that door.
Pretty much, yes. The confirmation using both JWST and HST means we can't easily blame the tools anymore. The discrepancy looks real.
So what does that force us to do if it's not an error?
It forces us to seriously consider modifying the Lambda CDM model itself. The standard cosmological picture needs tweaking, and it doesn't stop there. There's also growing evidence that dark energy might not be constant, not the simple lambda we assumed.
You send over that specific point data suggesting dark energy density might have dropped, what, about 10% over billions of years?
That's right. It's still being debated, of course, but if that holds up.
What's the implication of that, if it's dynamic?
Well, it means dark energy isn't just empty space energy. It has to be some kind of new time-evolving fluid or field, which, if true, completely changes how we think about the ultimate fate of the cosmos. It's a profound shift.
Okay, let's switch gears completely, from the huge scale of the universe down to the tiny scale of particles. Particle physics has its own major issue, right? The naturalness problem.
Oh, absolutely. At its heart is the Higgs boson. Its measured mass is just, well, it's confusingly light.
Why confusing?
Because based on quantum mechanics, its mass should be dragged way, way up by interactions with other particles,
Unless there was some kind of elegant cancellation happen.
Exactly. And for decades, the best candidate for that cancellation was supersymmetry. SUSY.
The idea that every particle has a heavier superpartner particle.
Right. These superpartners would naturally cancel out those huge quantum corrections, keeping the Higgs light elegant.
But the LHC, specifically Run 3, hasn't found any definitive signs of these superpartners.
That's the problem. The experiments have excluded huge swaths of the simplest, most natural SID-USY models. We're pushing the possible masses for these partners so high that, honestly, SID-USY starts to lose its original appeal. It needs fine-tuning itself, which defeats the purpose.
So if the elegant solution isn't panning out, where do theorists go? What if you just give up on naturalness?
That's the really dramatic pivot we're seeing. Some physicists are seriously exploring the string theory landscape.
The multiverse idea.
Sort of, yeah. The landscape suggests there isn't one perfect universe, but maybe countless possibilities, a multiverse. And our universe, with its strangely light Higgs, just happens to be the way it is because, well, that's where we ended up in this vast landscape. It's a bit like saying it is what it is.
Wow, accepting cosmic randomness instead of elegance. That's a huge conceptual leap.
It is, but while theorists are grappling with that, the engineers are just building things. It's the other side of the coin.
Let's talk about that sprint. Starting with materials science, there was a big breakthrough.
A really significant one, yes. Back in March 2025, the successful synthesis of a nickel oxide compound. The key thing, it showed high-temperature superconductivity, HTS, at ambient pressure, normal conditions.
Okay, why is ambient pressure the game changer? We've had HTS before, right?
We have, but mostly in copper oxides, often needing extreme pressures or conditions. This nickel oxide discovery proves HTS isn't limited to just cuprates. It opens up a whole new, potentially much larger family of materials to explore for practical superconductors. Think cheaper, easier to make HTS magnets.
And those HTS magnets are crucial for fusion energy.
Absolutely. Look at the public approach. ITER, the international project, is aiming for its first deuterium-tritium plasma around 2039, and that's still an experiment.
But in the private sector, things are moving much faster.
Dramatically faster, largely thanks to venture capital and these HTS magnet advances. Helion Energy is a prime example. They signed the first ever power purchase agreement for fusion power with Microsoft, a PPA.
And the timeline for that.
They're targeting a 50-megawatt plant online by 2028. That's commercial fusion power, potentially on the grid, in just a few years. Incredible acceleration.
And underpinning a lot of this progress, both in theory and experiment, is AI.
Definitely. AI is becoming fundamental infrastructure for physics. It even got recognized implicitly in the 2024 Physics Nobel for Machine Learning Foundations. We see AI controlling incredibly complex fusion plasmas in real time. We see it searching for faint signals of new particles and LHC data using anomaly detection. It's everywhere.
So wrapping this up, we have these two parallel stories. Deep, abstract theoretical questions, like the string theory landscape.
And incredibly concrete near-term engineering wins, like that 2028 commercial fusion target.
The sources also touch on geopolitics, China's push in quantum communication versus the US VC-funded fusion race.
Which leads to maybe the most interesting question for you, the listener, to consider. What happens next? We might realistically have commercial fusion reactors and powerful quantum computers within the next decade, real tangible tech.
Right.
But we could achieve all that while still having basically no clue what 95% of the universe dark matter and dark energy actually is.
Does the intense commercial race to apply physics force us to find the fundamental answers faster?
Or does the engineering world just get on with building things, leaving the deep cosmic mysteries unsolved? That's the tension to watch.